So I want to try to demonstrate a way of finding vector components that you probably haven't done before, but it's actually really useful when we get into two-dimensional motion, particularly circular motion. We don't often use it for projectiles, but we can. It's used a lot for, I don't know, orbits. Just it finds its way into all kinds of things. So we're going to use some new terminology. And this presentation might be a little clunky because I decided not to work with pencil and paper and pen. Instead, I'm going to work on my computer screen, which is me fumbling around with a mouse and a Google drawing. But what I liked about it is that I could snap a picture of the projectile app that you're using, and it could maybe just make a little bit more sense. So we'll see. I hope this doesn't go too long. I'm going to try to pause it in some places, maybe when I'm fumbling around. I'm going to try to avoid too much math. There's, of course, some equations to be done because it's vector components. It's, SOHCAHTOA. It's just that things look a little different. So anyway, what you're seeing on the screen here is a little snapshot of a velocity and an acceleration vector for the projectile that's, just any projectile flying through the air. We'll assume there's no air resistance. And so I'm using the color scheme that you see on the PhET app. And so I've just grabbed a snapshot here in time. And so what I'm going to describe here is how we find the components of not the velocity vector, but the acceleration vector. Now this should kind of make you a little confused because typically when we have a vector that's already vertical, we don't find its components. I mean, we already have its components. Or if we have a horizontal vector, we're like, yeah, we don't need the components. The components were only for situations where something wasn't horizontal or vertical. But in this case, it actually is more helpful to not have the vertical vector. We need components of that. It is a little similar to when you do inclined plane problems, which I think you've all done already. So on inclined plane problems, instead of talking about vertical acceleration or vertical forces, we talk about forces that go along the direction of the incline and perpendicular to the direction of the incline. Okay? So what we're going to do in a situation like this with motion is we find out how much of the acceleration is along the line of motion. In other words, in the same direction as the velocity. And then how much of the acceleration is in the other direction, the perpendicular direction to that, which doesn't really have a convenient name, but I'm going to show you what that looks like. So if it helps you, you could just pretend you're doing horizontal and vertical components. But what you'd have to do is kind of turn your head. Or this is one thing I like about working on this. Watch me kind of turn this. So I'm going to, again, my goal here is to take this yellow acceleration vector and break it into components so that one of the components is along the line of the green vector and the other is along the line perpendicular to the green vector, like this. So watch what happens. This is kind of cool. So I can rotate this. I'm going to do this until the green vector looks like it's horizontal. Okay. So I'd say just about there. So imagine I gave you this problem and I said, okay, take that yellow vector, which is not horizontal or vertical, and break it into components that are horizontal and vertical. I think you could probably visualize that a little bit better. But this one is just you're gonna have a hard time just kind of grasping visually what you're doing. So I'm going to do a little drawing here to help you with this. And this is what you're going to need to do when you do your own drawing, but you'll be doing it on pencil and paper. So anytime you find components, I absolutely encourage you to draw those components in with the original vector so that you can see how everything is oriented. That usually helps you see the right triangle. It helps you recognize the angle that you need to use in your equation. And without it, you're just kind of guessing. So don't try to take those shortcuts. So what I'm going to do, I'm actually going to pause this, and I'm going to I'll show you. I'm going to render a few things in the drawing, and then I'll show you kind of what you're going to do on paper. Okay, so you notice I've added to this diagram something that, again, I always recommend when you're doing vectors. Put little, very lightly dashed crosshairs of the coordinate axis through the vector that you're going to break into components. Okay, so whichever directions you would like to have your components, you'll have this little, crosshair shape. And in this case, it's skewed so that one of the directions is along the line of velocity and the other direction is perpendicular to it. Again, typically you see horizontal and vertical. or you might see along the inclined plane or perpendicular, but in this case, it's those other two perpendicular directions, okay? Okay, here's an important part. I want to introduce to you the two names that we give to these components, because we cannot call them x and y. We can't call them, parallel and perpendicular like an inclined plane. We can't call them vertical and horizontal. So we have two other terms that we use. The direction that goes along the line of the motion, or the velocity vector, is called the tangential direction, because it's actually tangent to the path or the curve that's being made by the object, in this case the projectile. The other direction we call the radial direction, or it's sometimes referred to as the centripetal direction, but we'll just use the word radial. So our components will be referred to as tangential and radial components, okay? So let me, again, reorient you so you can kind of picture this in a little more natural form. So I'm going to do this little rotation. If I just spin this a little bit to about there, it's going to look more like what you're used to with, if I say take that yellow acceleration vector and break it into this direction and this direction, you would say, oh yeah, there's horizontal and vertical. But again, we're just not dealing with horizontal and vertical here. We're calling them tangential and radial. And here's what's interesting. Those two directions don't stay fixed in space. Like tangential means whichever way it's moving at that moment. So that's why we need a snapshot. And this snapshot in a few minutes or a few seconds, this velocity vector will be more vertical because this is a projectile on its way down. So what's tricky about this is your components change at every moment. And so it's a little bit cumbersome to try to figure out what the components are all the time. Okay? So next I'm going to actually draw in the components. In fact, let's just go ahead and do this. So I've got a little, again, I'm doing this all with digital ink. So the idea of components is you draw the vector from the point of, let's see. I need to get this back to the front. All right, let me pause here. There we go. Okay, so we draw vectors back starting at the tail of the vector we're breaking up. And we draw it along the two perpendicular directions, the dashed lines that you drew, and you draw it just long enough so that it becomes the side of a rectangle for which your vector, your original vector, is the diagonal, okay? Or you could say it becomes sides of a right triangle for which your original vector is the hypotenuse, whichever way you'd like to visualize it. So it's a question of like, okay, how long do you want to make this thing? So this right now is way too short. It's not going to be the side of a right triangle with this as the hypotenuse. So we move this down, and we're going to go about maybe that far or so. And then I'm going to draw the other component, and we'll see where it ends up. Okay, so I've started drawing my radial component now, and I chose to kind of think in terms of the rectangle method. And so if you do it that way, you draw it just as long as you would for you to imagine a rectangle with this yellow vector and then this the two kind of thin ones being the sides, and then the other two sides of the rectangle aren't drawn, but they're just identical to these two. So I think it's probably easier to first picture it as the sides of a triangle. See? And I'm actually a little bit off here. So that tells me that this one was a little too long. So I'm going to reduce the size of my tangential one, and then I'm going to move this up. What's really important is that my two components have to meet at 90 degrees. That's what makes them components. So this, what I'm circling right now, that has to be my right angle. That makes my original acceleration vector the hypotenuse. And so I feel like that's a pretty good right triangle. So now, and I've seen people draw this in very lightly on their paper, since you're not using digital ink, and then just sketch its twin in the right spot here, because I really do think it's better if you have them kind of where they belong, so all the tails are meeting. This is the preferred way to show components, right? So so there they are. There's what the components look like. Again, we would label them. In fact, I'm going to put labels on them. A sub R and A sub T. You use X and Y for horizontal and vertical, but we're going to use radial and tangential subscripts to describe these. Okay, so I put some labels on these, which again you would want to do so that you remember what's tangential or along the line of that the motion at that moment, and then the perpendicular direction, also called the radial direction. Okay, So now we got to figure out which way all of this stuff is pointing. Okay, so we're close to being able to calculate the size of the components. Now, of course, we'd have to know what the size of the original vector is, but I think you'll know that. And we also need to know the angle that everything's making. So in a typical situation, you'll have enough information, like in this case, to figure out what angle your velocity vector is making. Now, you'll have to know what the components are, but once you know the components of the velocity vector, and I'm talking about the components relative to vertical and horizontal, you can use a little trig to figure out what angle it makes. So I just kind of picked a number out of a hat, and it doesn't quite fit right as far as the diagram, but I'm going to say maybe this is a 25-degree angle. So we would say at this moment, the velocity vector is pointed 25 degrees below horizontal. So if we know that, and if we also know the direction the acceleration vector points, which in our case is straight down, then the difference between those is what we need to use. So if we know this is 25 from horizontal and this is straight vertical, then the remaining angle, and I always put little arcy things in here, I wish I knew what they were called, that would be a 65-degree angle in there, because obviously this dashed green line and this vertical line have to make 90 when we put them together. So that's actually the last thing that we need, because remember, let me do something you can't do on your paper. Well, you could do this lightly on your paper. Draw an extra little vector over there, because then it starts to look more like what you remember from geometry class. I mean, here's a right triangle, right angle here, hypotenuse here, and a 65-degree angle down there. That's set up perfectly for SOHCAHTOA. The length of the hypotenuse times the cosine of 65 will give you what we are calling our tangential component. And then to get the radial component over here, which is opposite the 65, we would use the hypotenuse times the sine of 65. Okay? And so those would be the sizes of each of them. I'm not going to actually do that math because I don't want to take any more time. Let me put this back kind of where I like it to live. And again, I'm okay with you drawing light little lines. I call them little auxiliary lines or supplemental lines, just to help you. Dash lines, whatever it takes to help you visualize things. Because, again, this is not the easiest thing to visualize. So at that point, we would have our numbers for those two components, and that's kind of what we're after. So, I mean, golly, we're at about almost 13 minutes here by the time I'm done. So hopefully this was enough to help you visualize this. Yours will look a little bit different. The one thing I will add is that sometimes the component of your acceleration is going against the velocity. It's actually going opposite, rather than here where it's kind of directed along the same direction. That is a case where we say it's a negative tangential component. Okay, kind of a typical way when accelerations and velocities are opposite each other. We usually say they're oppositely directed, or one's negative. Same idea there. We don't ever have a convention for the radial. There is no positive or negative direction for the radial. But the positive-negative convention for tangential is anything with the motion is positive and against the motion is negative. Okay, that'll happen if the angles between there is more than 90 degrees. All right. So, all right. So I'll leave it there. Here now, I'm approaching 14 minutes. And if you have more questions, a little difficult to ask questions, I know right now, but hopefully this was enough detail that you can kind of figure out the components that you need to figure for yours. So, all right, we'll call that a wrap.